Hello everyone, today we're going through a homework question from my Organic Chem 1 class. So this question asks, consider the following changes to the rate of the reaction. So here's the reaction here. Things we want to notice is the primary alkyl halide, right? This is, DMF is polar aprotic, right? Polar because it doesn't have nonpolar bonds, and aprotic because it doesn't have any acidic hydrogens. So this is a polar aprotic solvent. And our nucleophile here is methoxide, right? So methoxide, we know, strong base, strong nucleophile. It's probably going to prefer a bimolecular alkyl halide reaction, specifically because we have a polar aprotic and that this alkyl halide is primary. This is going to follow an SN2 reaction. Quite simple here. Iodide's like, give me them electrons. Methoxide's like, my alkyl halide now. Or not really alkyl halide, but my carbon now. And that just gives us kind of the same molecule, but with methoxy group on it, added on. So the two scenarios we are given to consider how it may affect the rate of change is, one, if we change the solvent to isopropanol, and two, if the alkyl halide reactant is changed to 1-chloro-3,3-dimethylbutane. Let's start with number one here. So we're changing the solvent to isopropanol. So we need to compare DMF to isopropanol. What are we changing here? Well, what you'll notice is that we go from polar aprotic to polar protic. So I'll write that here. This is a polar protic solvent. What does this mean? Well, this hydrogen here, I'll elaborate the bond. It's acidic because it's bound to the electronegative oxygen here. That gives us a dipole like that. So oxygen's like, well, if there's something out there that could steal that proton, I'm kind of happy with that. And I'll take the electrons, no problem. So this is a polar protic solvent. So what does that mean? Well, the rate of the reaction here is going to go down following an SN2 mechanism. It probably won't even. It'll probably pick, depending on the conditions you give it, SN1 or E1. So for that reason alone, just changing the solvent is going to really significantly decrease the rate of that reaction there. We're going to decrease the rate of the reaction. As for an explanation why, if you have a polar protic solvent, let's consider what it would do to the methoxide nucleophile. So let's just say this will act as a base, right? We know that because of the negative charge on the oxygen. Oxygen is fairly electronegative, but it will still make a bond with hydrogen to act as a base. Something important here to notice is that if solvent, there's lots and lots and lots of atoms there, right? Because it's the solvent. So what it's going to do, potentially, is interfere with this nucleophile here, protonate it, therefore decrease the rate of the reaction here. So that's kind of an explanation as to why. For number two here, an alkyl halide is changed to 1-chloro-3,3-dimethylbutane. That's the molecule there. The only difference we see here is that we're changing the leaving group from iodide to chlorine. So what does that mean? A lot of students can get really tripped up here when we look at the better leaving group. We might think electronegativity and automatically assume that chlorine's going to be the better leaving group, but that's not really the case, and I'll explain why. So let's kind of just compare chlorine in a simplified drawing. We'll draw that a little smaller. That's a little too big. I'll run out of space. Here's chlorine's atomic radius. Here's iodide. You'll notice that chlorine is a lot smaller than iodide. So when it leaves, it's going to bear an extra electron on it. So we'll just draw it here. Well, iodide's a big fat atom, so it's like, okay, fine. I'll take on the negative charge. I'm okay with that. But chlorine, it's not as bad as fluorine, but chlorine is still like, oh, I don't know about holding that negative charge when in comparison to iodide. So think of iodide as this big fat person that's like, I am happy to have that electron. I'm happy to leave this compound because I'll get an electron and I can store it within my big fat body. But chlorine there, it's like, I don't really want to do that, you know? because it's a lot smaller, it can't handle that negative charge as well as iodide can, which is a little counterintuitive when you take into consider electronegativity. So what will this do? Well, if iodide can be more stabilized holding that negative charge, well, that means that it's better to leave, right? Better than chlorine can. So instead, if you use 1-chloro-3,3-dimethylbutane over the iodide one, it's going to decrease your rate of reaction because iodide's a better leaving group than chlorine is, right? So the rate of the reaction here, your rate will go down. Very sad, very sad. So just to summarize, we have this reaction mechanism, follows SN2. You use a polar protic solvent instead of a polar aprotic solvent. It's going to decrease the rate of the reaction, possibly even favor SN1 or E1 reactions. Number 2 here, the alkyl halide is changed to 1-chloro-3,3-dimethylbutane. You're using an alkyl halide with a worse leaving group of chlorine. Because of that, chlorine isn't going to want to leave as much as iodide is, so the rate's going to go down. That's that question for you guys. Hope you guys enjoyed this video. Hopefully I explained everything in a good enough way for you. And have a good day. Goodbye.